Quantum computing. You've probably seen the headlines, right? They promise a future that sounds like it's straight out of science fiction. We're talking miracle drugs, unhackable codes, and a complete revolution in, well, pretty much every industry. Tech giants, governments, they're all betting billions that this future is right around the corner. But is it? Today, we're going to dig in and separate the incredible quantum hype from the often harsh quantum reality.
To even begin to unlock this world-changing power, you have to start with an absolutely insane challenge. Take a look at this number, negative 273.15 degrees Celsius. That's absolute zero. It's colder than the deepest, darkest corners of outer space, and it's the temperature you need to keep some of these quantum computers from literally shaking themselves apart. This one number, right here, captures the entire story perfectly. A promise of immense power met with an equally immense, almost impossible level of difficulty.
And let's be clear, that promise, it is staggering. We're not just talking about faster computers. We're talking about the power to design revolutionary new medicines by simulating molecules from the ground up, the power to invent new materials that we can't even dream of today, or building financial models that could predict the chaos of the market with scary accuracy. This is the why. This is the reason for all the buzz and all the billions being invested.
Okay, so what is actually going on under the hood of these incredible machines? To really wrap our heads around the hype versus the reality, we've got to start with the basic science that makes them tick, and let me tell you, it gets weird.
So let's dive right into the core science. If you want to understand a quantum computer, first you have to understand the truly strange language that it speaks.
Every single computer you've ever used, your phone, your laptop, everything, speaks in a language of bits. Think of them as tiny little light switches. They can be on, which is a 1, or they can be off, which is a 0. Simple, reliable. But quantum computers, they use something called qubits, and this is where reality kind of starts to bend. A qubit isn't stuck being just on or off. Thanks to the bizarre rules of quantum mechanics, it can be a 1, a 0, or, and stick with me here, both at the exact same time.
This frankly magical property is called superposition. The best way to think about it is like a spinning coin. While it's spinning in the air, is it heads or tails? Well, it's neither. It's a blur of both possibilities at once. It's only when you catch it, when you measure it, that it has to pick a side. This ability to hold all these different values at the same time is what lets a quantum computer chew through a massive number of calculations all at once.
And if you thought that was weird, hold on. The second piece of quantum magic is called entanglement. Even Einstein was freaked out by this. He called it spooky action at a distance. Basically, it's this mysterious invisible link between two qubits. If they're entangled, they're connected, period. If you measure one, you instantly know the state of the other one, even if it's on the other side of the galaxy. And here's the kicker. This is why their power grows exponentially. You add one more qubit, you don't just add a little power, you literally double it. So you take these two mind-bending concepts, superposition and entanglement, and suddenly you can see why we get these wild, incredible headlines. They create this feeling, this perception, that a full-blown quantum revolution is just waiting to happen any day now.
But, and this is a really big but, all that incredible potential runs headfirst into a wall of harsh reality. The journey from a wild physics idea to a stable, reliable machine is proving to be one of the most difficult engineering challenges we have ever faced.
You see a headline like this one, right? Quantum computers just beat classical ones exponentially and unconditionally. Wow, it sounds like the race is over. Game won. It's exciting, it's dramatic, and it sure makes it sound like the world has already changed forever.
But then, you have to look at the reality. This list right here, this is what keeps quantum engineers awake at night. First off, qubits are unbelievably fragile. The tiniest vibration, the smallest change in temperature, and they lose their special quantum state. It's a problem called decoherence. And that fragility leads directly to the second problem, error rates that are millions of times higher than the computer you're on right now. Then you add in that extreme cold we talked about, the sheer difficulty of actually adding more qubits, and yeah, the multi-million-dollar price tag for one of these things. Suddenly you get a sense of just how big this challenge really is.
So it's no surprise this leads to some pretty heavy skepticism, especially from people deep in the field. While the big headlines are celebrating breakthroughs, you can go on Reddit and find comments like this one, someone basically arguing it's all wishful thinking and will never work. It's a powerful, sobering reminder of the massive gap that still exists between the theory and the practice.
And look, this isn't just some abstract debate for physicists in a lab.
because if we do manage to overcome all these challenges, the power we unlock is going to have real consequences for every single one of us. The stakes are very, very real, and they're not some far-off sci-fi problem.
Because with all that future power come very present risks. We have to start thinking critically, not just about what quantum computers can do, but what they should do.
The potential applications are absolutely astounding. Of course they are. Quantum computers could help us discover new drugs, totally optimize financial markets, create AI that's way more powerful. But that third point on the list is the one that really worries security experts: cracking today's encryption. A powerful enough quantum computer could, in theory, break the very security that protects everything from your bank account to national secrets. Deloitte actually has a great framework for thinking about these risks. First, quantum threatens the protections we already have, like encryption. Second, it could make the problems we already deal with even worse, like supercharging an AI's ability to harvest our personal data. And third, it could create brand new risks we haven't even thought of yet, especially in tricky fields like gene editing.
It's this double-edged sword, this incredible potential for both creation and destruction, that has turned quantum research into a fierce global competition. You'll hear a lot of people calling it a new kind of arms race.
And the numbers here are just staggering. We're talking billions of dollars being poured into quantum R&D by all the major world powers. For them, this isn't just about cool science. This is about future economic power and national security. In the quantum race, absolutely no one wants to get left behind.
So, where does all of this leave us? You've got the hype, you've got the immense challenges, and you've got a global race to the finish line. What does the path forward from here actually look like? Well, a realistic timeline is key to managing expectations. Right now, today, quantum computers are basically just research tools in a lab. Maybe in the next 5 to 7 years, we can hope for more stable qubits, but solving actual, large-scale problems for big companies, that's likely still a decade away, maybe more. And as for widespread, everyday use, we could be talking decades.
And this is so important to understand. We've got to bust one of the biggest myths out there. Quantum computers are not going to replace your laptop. The future is hybrid. It's about teamwork. Classical computers will still do all our everyday stuff. Email, browsing, Quantum computers will be like specialized accelerators, the heavy-duty tools we bring in to tackle the specific, impossibly complex problems that only they can solve.
So, the crucial takeaway here is this: quantum computing is not science fiction. The principles are real, the progress, while slow, is undeniable. But that revolution that you keep reading about in the headlines, that's not here yet. We're still in the very early, very challenging, foundational days of a whole new era of computing.
So make no mistake, quantum is coming. It's going to be a slow and difficult road for sure, but we are on that road. So the question we really should be asking ourselves isn't, when is it going to get here? The real question is, when it finally does arrive, are we going to be ready for it?